Hello, my name is Angel Sunya. I would like to share with you my experiences, which I hope will help you in your daily work. I prepared 4 videos. We'll go through 3 different controllers, PI, and PID controller. And we are interested in the following processes: air conditioning, heating, and domestic hot water preparation. We'll use process of domestic hot water preparation to explain each type of controller. Here is a block diagram of this process with static characteristic of each component. One of them is also controller. The P controller acts as an amplifier with the gain Kp. The output signal is proportional to the error. So we say that controller has a proportional action. Output signal looks like this, but we know that most of the actuators have standard input 0 to 10 volts. That's why we move 0.45 volts and we get this characteristic. Or generally speaking, we have this kind of graphical presentation of P controllers, and we see that for the output 0 to 10 volts, we need on its input a certain error. In our case, when the proportional band is 20 degree, we need an error of 0 to 20 degree. And we can reduce an error to reduce a proportional band. But we must be careful, because with a too low proportional band, system can become unstable. So what are the features of P controller? Responds very quickly on error, but needs an error for its operation, so it is not accurate. How P controller works together with heat exchanger. Here is a static characteristic of heat exchanger, and our reference value in our case is 15 degree. And here is a characteristic of P controller with a proportional band of 20 degree. It means that temperature will change with consumption from 40 to 60 degree. If consumption increase from 800 liters to 1000, there is an error. And controller open the valve in order to reduce an error, but it doesn't eliminate it. So still is there an error of 2 degrees. And it is the same story for further on. If there is a next increase of consumption, there is also action of controller to reduce an error. On the end, when the system reaches the nominal value of consumption, there is an error of 10 degree. So we can reduce the errors by reducing the proportional band. But we must be careful, as we said before, because the system can become unstable. We are looking for controller that eliminates the error. This is PI controller. It has P and I component, and it is the controller that eliminates an error, and that is very widely used controller. P component has proportional action, but I component has an integral action. And when there is a step change of error, then the integrator increase its output signal as long as there is an error on its input. And the slope of the rise depends on the current value of the input. It means the current value of step change in our case. When the error reaches a value of 0, then the output rise stop and the last value is maintained. The parameters that can be set in PI controllers are proportional band for P component and integration time for I component. And what is integration time? This is the time the integrator component has to contribute the same amount to the controller output as the proportional component. How PI controller works together with heat exchanger. Here is a static characteristic of heat exchanger and a characteristic of proportional component. And if the consumption increase, then there is an error. P component reduce an error, but there is still an error present, which is eliminated by integral part, which is integrating based on this error input, and eliminate an error completely. And further, if there is a further increase of consumption, it is the same story. First react proportional component and integral part eliminate an error completely. And we see that when there is a nominal consumption of 2000 liters per hour, the primary flow is 1800 liters per hour. But when we used peak controller only, there was only 1400 liters per hour. Here are typical processes where PI controller is used in domestic hot water preparation process and channel temperature control. Here is a process of room temperature control. In this case, in this application, the time constant of the process is very large, and therefore response times are very long. So in such processes, we usually use cascade control. P plus PI control, or with other words, cascade control. In this case, we introduce additional temperature measurement in flow channel and additional P controller. So it is so-called nested control loop introduced. And this P controller has a very low proportional band, and so the error is very low. And its input is the output from PI controller, which is accurate. And this small error, which is caused here with P controller, is eliminated by PI controller. What are the features of PI controllers? React very fast on error, and it is a controller that eliminates an error completely. So it is very accurate. It is the most often used controller, therefore. And there are also some disadvantages, and one of them is oscillatory response, which means that that integral component reduce the stability of control system because of this overshooting response. And there is also another phenomenon which is also a disadvantage of this controller, which is known as reset windup. It appears at the beginning when there is a large error value, and then I component enters to saturation, and we can avoid this saturation that in that way that we shut off the I component and at the startup, and then switch it on again when the system becomes stable. By adding D component to PI controller, we obtain PID controller with D component as a derivative component, and it is proportional to the derivative of the error. The output of D component is proportional to the rate of change of the error signal. So by deriving the error, which can be graphically presented as a tangent in a certain point, this component predicts the direction of its motion, of the motion of error. And this is useful for some processes. And generally, the purpose of derivative action is to improve the stability of the control system. But the action causes problems when the error changes quickly. From shown diagrams, we can see that derivative actions try to work opposite of where the proportional and integral part are trying to drive the process. It is like a brake, therefore. And therefore also the Chi-P can be a little bit higher and response therefore faster. And the right amount of derivative action can stabilize the process variable sooner. There is a parameter TD, derivative action time, which is specified. It means that TD is the time it takes for the P component to reach the value of D component. From the shown diagrams, we see that transient response of all three types of controllers and the PID controllers achieves the desired value faster. And there are some disadvantages of PID controller. It is difficult to set the optimal value of three parameters. Well, two, it is easy, for example, for PI controller, but there is a third component, TD, so it is difficult and it is not suitable for all type of processes. In some literature, it is written that D means also don't touch. How to find optimal settings of controller parameters? We'll present Ziegler-Nichols method, which the process is in that way that first of all we need to switch off I and D component, and then we try by reducing the proportional band to make system unstable. And for each value of proportional band, we just make a graph, and this is a graph where the system is very stable, and this is a critical stable situation, and here is the system is very unstable. And what is interesting for us is this one is the middle one, when the system is in critical situation, and the proportional band is in that case critical proportional band. So if we know this critical oscillation time and critical value of proportional band, we can find here in this table what should be the optimal parameter for different type of controllers. So that's all. Thank you very much for watching, and I'm looking forward to meet you in next video.